Okay, now we're going to talk about a concept we call vapor pressure. There we go. My pen actually started writing. So what happens in vapor pressure, let's take a container. Let's pretend that's like normally drawn, and let's put a lid on it. It doesn't have to have a lid. Vapor pressure is still a concept without that, but we'll talk about this context. Let's put a liquid in here. And then, because we have a liquid in a closed container, or even an open container, right? In our liquid, some of the molecules, when they reach the surface, are going to try to escape. So, some liquid molecules vaporize. So they become gas. So some liquid molecules vaporize. In the previous video, we talked about the fact that eventually you would reach what was called dynamic equilibrium, where every time a molecule would reach the surface and try to leave, another one would be colliding with the surface and rejoining it. And that's because you were at a rate where the rates were equal. So for a while, if you were to first start this experiment, like you took a water bottle and you closed it, and it didn't have much water vapor at the top, initially you would just see, well, not see, but there would just be water molecules vaporizing into the gas phase. But as more water molecules entered that gas phase, there would be more collisions with the surface, and you'd be more likely to get some of them to reform into the water and condense back down. Given enough time, molecules would vaporize as fast as they would condense. They would both be changing at the same rate, so the net case would be that there wouldn't be a change. Now, when you're in that condition where they're going back and forth in equal amounts, there are some molecules in the gas phase. Like we learned back in 1211, those molecules, because they're a gas, have to exert a pressure. So the partial pressure of those is what the vapor pressure is. So vapor pressure, another way to word that is going to be the pressure exerted by the vapor when in dynamic equilibrium. So when it's allowed to reach equilibrium, what's going to be the partial pressure of the gas molecules of that substance? That's going to be its partial pressure. Now, what's going to impact this vapor pressure? So some things to think about are strong intermolecular forces. So I'm just going to do a little thing over here. So if you have strong intermolecular forces, that means that the molecules are attracted to each other. They're more likely to want to stay in the liquid phase. It's going to take more energy to overcome those attractions, so it's harder to escape. So that means if your intermolecular forces are strong, you will have a low vapor pressure. Vapor pressure. And the reverse is also true, that if you've got weak intermolecular forces, it's going to lead to a higher vapor pressure. The next thing that happens is that this is temperature dependent. So as you increase the temperature, your vapor pressure increases. And the reverse is also true, that if you were to decrease the temperature, the vapor pressure would decrease. This is because the molecules are getting more energy, and since they have more energy, more of them are going to have enough energy that when they hit the surface, they're able to escape, like we talked when we were talking about vaporization as a process. So that means that as temperature increases, our vapor pressure is going to increase. And as our intermolecular forces get weaker, our vapor pressure gets higher. And that's important because that's different than a lot of the other features we talked about. In our other impacts of intermolecular forces, usually the things went up, right? So like viscosity got higher as intermolecular forces got stronger, and our capillary forces got stronger, and our surface tension got higher. So just keep that in mind, that if a problem asks you which of these is going to likely have a higher vapor pressure, that's a way of asking you which of these is going to have weaker intermolecular forces, assuming the temperature is constant. Now, eventually, you reach the boiling point. So let's talk about boiling points. So not worrying about chemistry, but just in general, you know that, like, for example, if I put some water on the stove and I heat it up high enough, eventually if it reaches 100 degrees Celsius, or somewhere close to there, it's going to be high enough that it reaches the boiling point. And then bunches of bubbles come out and it starts turning into steam. Very, very rapidly. What's happening at the boiling point is once you reach there, the vapor pressure is going to equal the external pressure. So for example, if you are at sea level your atmospheric pressure is going to be 1 atmosphere. So once your vapor pressure hits 1 atmosphere for your particular substance, you raise the temperature enough to get to 1 atmosphere, you're now at the boiling point, and it can now readily boil. So what's happening there is, say to put it, is that now it's not just at the very surface of the liquid that you can get vaporization, like we talked about earlier. Now it's everywhere inside of there. That's why you get these little bubbles to form, and that when you see when boiling, is it's not just trying to leave into the gas form when it hits the surface and tries to escape. It's everywhere in the substance. It's everywhere trying to form these gas molecules and escape out. Not just right at the surface, but like inside. Like if you've ever watched a pot of water boiling, if you're looking at it, you'll notice the bubbles, it's not like they just form at the top. They form down near the bottom as well, and then they rise up and are able to escape that way. So once you hit the boiling point, it's trying to escape at all parts of the liquid, not just right at the surface where it's vaporizing. What was the other thing I wanted to mention? Oh, right. So a common term you may hear, and we're going to use in a few problems, is something called the normal boiling point. So this is just a way of saying, so this word normal here, if you may remember from 1211, is just a way of saying you're at 1 atmosphere. So it's whatever the boiling point is. So this is the boiling point, BP, at 1 atmosphere pressure. So that's for the external pressure. And that also means that since we say that it depends on the outside pressure, that if you go to locations at different heights, that's going to cause there to be different boiling points. So for example, you get, let's say all the way on top of Mount Everest. That's nice. The highest point we've got in the United States, not in the US, oh my God, I'm bad about this. The highest point we have that you can reach on Earth. Clearly not in the United States. So Mount Everest is going to be high enough that the boiling point, I've checked my notes, is 78 degrees Celsius. It's got an elevation of 29,035 feet. So it is high enough up that you're able to lower the boiling point by 22 degrees. Now, most people aren't going to be trying to go to the top of Mount Everest. Let's just look at Denver, Colorado instead. That's probably the most common U.S. example of a place that's got lots of mountains. It's really up high. The whole town is elevated. It's elevated at, let's see, Denver is about 5,000 feet above sea level, and so it's got a boiling point of water of around 94 degrees. So that means you're going to be at a cooler temperature. The effects of pressure are why if you actually ever check certain types of cooking directions, especially for baked goods, they'll have slightly different directions for high altitude cooking. And the reason high altitude cooking would be different than low altitude cooking is related to these pressure effects. So one really common example is if you're worried about boiling water, it's going to boil at a different temperature, which will change some of the properties of like what you're doing. You're not able to cook it the same way, or you might need different cooking times because you're at a different temperature there. There are some other properties that get changed because of the pressure as well. But it's just nice to recognize, yes, there are things people do that like, not that chemists aren't real people, but like things everyday people do that get impacted by pressure. It's not just something we do inside a lab and look at for stuff. It's something that you actually come across. So that's our boiling point. Now what we want to get into here is something called the Clausius Clapeyron equation. Okay, I've got a problem coming up, so I'm going to write about it here, and then we'll talk about our problem. So the Clausius Clapeyron equation, I think I'm spelling this right. There's a chance I'm not. If you try to Google it and it corrects, like where I think I'm Oh yeah, that does appear to be right. Clapeyron. That's one word, not two words. It's not Clapeyron. Clausius Clapeyron equation. So what this does is this is a relationship that forms, it turns out, between the natural log of pressure versus the inverse of temperature. These two things have a linear relationship. So specifically, if you try to relate these, you'll get the equation natural log of P equals negative enthalpy of vaporization over R times 1 over T plus the natural log of beta. Something you may or may not notice, and if you don't notice it yet, you will by the time we get through this class because we're going to keep doing this over and over again. This is in the form of Y equals mx plus b. I can't remember if they uppercase or lowercase the b when they do it in algebra. So this is a linear equation. We like linear equations in chemistry because we can use some of the properties you've learned in math about them, like information about the slope is really easy to interpret. This is why when we talk about vapor pressures and we start talking about the enthalpy of vaporization, we're many times going to work with not pressure versus temperature, but natural log of pressure versus temperature. This is where we're taking a relationship that is exponential and we're turning it into a linear relationship because we have better intuition about linear relationships and we've got some math we can do on them that we can't do in some of the other cases. So it's a really useful form. This will not be the only chapter we do this. We do this 3 separate times, I believe it is. We have 3 different equations that are going to look really, really similar to this. So this relationship you're also going to work on if you're in my course. You're going to work on it in lab as well. We'll do some measurements. We're going to measure some temperatures and some pressures, and you're actually going to find this relationship of what enthalpy of vaporization is. And in case you don't remember, don't forget that the enthalpy of vaporization is how much energy it takes for the molecule, the substance, to transition between the liquid and gas phase. Because it's not, once you get up to that temperature, like a boiling point, it takes a certain amount of energy to make that transition. The enthalpy of vaporization is a measurement of that. Also, I'm going to make my face disappear for a second. It's helpful to remember that R is our universal gas constant. We use it a few different ways, but here we're going to use it as 8.314 joules per mole Kelvin. We do this because it's going to work out unit-wise. If you tried to use liters times atmospheres, that version, it's not that that's not a true value for R, but the units aren't going to cancel out correctly with your enthalpy of vaporization. So this form of R is the same idea, it's just we're using in different units. There have been a lot of conversions that go on. So we'll use this version. I also want to highlight that you need to pay attention to units because R is usually reported in joules, whereas enthalpy of vaporization is many times reported in kilojoules. So you need to make sure that they match before you try to put them into a calculation. Now, we've got a problem that we're going to solve, which is what is the vapor pressure of benzene at 70.5 degrees Celsius if benzene has a heat of vaporization of 30.72 kilojoules per mole and a normal boiling point of 80.1 degrees Celsius. Before we can solve this, though, we need a different version of our equation. So the version I showed you on the last page is useful when we have a whole bunch of data points and we make a graph out of it. And we can get some information from that because it forms a linear graph. We get our y equals mx plus b. We can set it up to help us figure out information. But sometimes we might have something like this where we just have 2 data points. This isn't enough information to figure out what that L and B term is. So we can do some rearranging and you can get a form of the Clausius Clapeyron that looks a little bit different. It's the most common form to see on, for example, general chemistry tests because it's easier to plug in. It doesn't require us to have a graph to interpret. So if you've got a graph, you'll see the first version. But this is something called the 2-point form. So for this, we get the natural log of P2 over P1 equals negative enthalpy of vaporization over R times 1 over T2 minus 1 over T1. Note that you might see a slightly different version of this if you look up in a few places, and that's just because your rules of logarithms allow you to do things with negative signs. So we're going to go over this more in another example we do with natural logs, but just in general, remember that if you had something like the natural log of x equals some value y, what's important is this negative sign here is like a -1, and when you have a value in front here, you can move it to the power on your logarithm. So this is the same thing as saying the natural log of x to the -1 equals y. Well, x to the -1 is just ln 1 over x. So what happens is sometimes people will do things like flip the P2. I'm going to bring back my webcam. They'll do things like flip the P2 and P1. You also could have P1 over P2, but then there'd be a negative in front of it. But then maybe you move the negative to the other side. So there's a lot of rearranging that can happen. And I say this because I know as a student sometimes you might see a version that looks really similar but a little bit different, and it's easy to think initially, well, they're just wrong. They're not doing this right, or Dr. Leslie told me wrong, or something like that. It could be they've just done a bit of rearrangement. I also mention that because this 2-point form, you're going to see 2 or 3 equations that look like this as we go to future chapters. As we get to the topics like equilibrium, it's going to come back up. It'll have some different variables, but it's the same idea of we're linearizing an exponential. So now, let's take this equation and figure out how the information up above lets us solve that equation. Because initially it might look like, Dr. Leslie, I definitely don't have enough values. So what we're going to do is we know we're given 2 temperatures. We're given a delta H of vaporization. So initially it looks like, okay, I've got 2 T's and I have a delta H. But I don't have any pressures. How can I solve this if I have 2 variables? But you do have a pressure because it tells you normal boiling point. That's a fancy way, not really fancy way, but it's just a way of telling you that's it at 1 atmosphere of pressure, or 760 torr if you want to work in torr. So for my variables, I'm going to assign P1 as equal to 1 atmosphere. You could assign P2 to 1 atmosphere. Works just fine. You just have to be consistent with your T1 and T2 as well then. So if P1 is 1 atmosphere, T1 is 80.1 degrees Celsius, which I'm going to go ahead and convert to Kelvin. I really should be able to add 273 in my head just fine, but I'm going to calculate it using 353.1 Kelvin. I only added 273. If you add 273.15, that's fine as well. That'll be slightly more accurate. This was just what I was doing initially in my work. So then we have P2. We don't know that. That's our variable of interest. And then T2 is 70.5 degrees Celsius. And to that 70.5, we're going to add 273. I know I can do it. Oh, well. Didn't do it in my head, so I'll just write it down. 343.5 Kelvin. And then finally, our delta H of vaporization, I'm going to go ahead and write it as 30,720 joules per mole. You don't have to do that. You can make the conversion later, or you can convert R to kilojoules. I just like doing it here. I like changing my enthalpy vaporization, so that's what I'm going to do. Also, it helps if I've got a consistent pattern. It means I won't forget that stuff. So now, we got some values to plug in. So I've got the ln of P2. Because P1 is 1. So P2 divided by 1 atmosphere divided by 1 is just P2. Is equal to negative 30,720 joules per mole divided by 8.314 joules per mole Kelvin times 1 divided by 343.5 Kelvin minus 1 divided by 353.1 Kelvin. So now we've got a lot of things to plug in. Also, I'll point out these joules per mole are going to cancel here. And actually, the kelvins are going to end up canceling out as well. Because here, we're doing, this is no unit on top, 1 over Kelvin on bottom. That means it's going to become Kelvin on top. Since 1 divided, I'll just do it to the side. Since 1 divided by 1 over K is equal to K. You're just inverting it, basically, because it's 1 divided by 1 over X would be X. Then you're multiplying it by, these two things are a difference here. So the final answer for that is going to be per Kelvin. So Kelvin times per Kelvin. So, bye screen, I'm leaving. I'm still here, obviously. So Kelvin times 1 over Kelvin, those just cancel. We're going to get no unit on the right side. This makes sense because when you take your natural log and you want to undo it, you don't want any unit on the right side because there's not going to be something to work with. And that's why actually initially I'll keep this over 1 atmosphere for now to help us remember that P2 is eventually going to be in atmospheres. Now, I got a bunch of things, and I'm going to come back because I don't have to have that part blocked right now. There we go. So now I've got a bunch of things to put in my calculator. So we've got 30,720. Well, it's negative. Don't forget your negative sign. We're dividing it by 8.314. And then we're multiplying it by the difference of these two temperatures. Make sure you're careful with parentheses when doing something like this, because that's a really common place to have issues. So here we have the natural log of P2 over 1 atmosphere equals, let me check something real quick. Yeah, that answer is reasonable. So if I multiply all this out, I got negative 0.29, I'm going to say 25. I'm only going to have 3 significant figures in my answer, but I kept an extra digit. Did I make sure? Yeah, I'm copying the right place. So I like to keep a little bit more, and I'm honestly just going to keep the whole number in my calculator. I have like 10 digits when I'm solving it. The reason for this is as we start to have exponentials and logarithms, it can cause really large shifts for very tiny changes. So we want to be careful with those. So now I'm going to get rid of my natural log. I'm going to raise both of these to the power of an exponential. This e and ln that are next to each other will cancel, and we'll end up with, this all leads to P2 over 1 atmosphere equals 0.746. So I'm at the end, so I'm ready to round, so I'm just going to put it to 3 sig figs. Now, I can multiply both sides by 1 atmosphere, and 1 doesn't change anything, but it does give me my unit. P2 equals 0.746 atmospheres. The vapor pressure of benzene at 70.5 degrees is going to be this. A nice check that's also helpful is that notice this temperature is below the normal boiling point. That means the pressure should have gone down because lower temperatures decrease the pressure. If this pressure were greater than 1 atmosphere, it would probably mean that I made a mistake somewhere in my problem. So it went down, it's below an atmosphere, that's good. The second comment I want to make, because this can be confusing depending on the numbers you're working with. This decrease in vapor pressure is not a linear function. The reason this matters is sometimes you might get a really, really small number, even if you don't go down that far. Like if you went down to 50 degrees, you might get, I'll admit, I have no idea what the vapor pressure of benzene at 50 degrees is, but you might find it something like 0.2 atmospheres or 0.1 atmospheres, and that might feel really weird. It's okay to have drastic shifts downs as you go down in temperature, because it is an exponential function. You're going to see really vast decreases sometimes. Now, it depends on the exact aim of that exponential, how close you are to the temperature of the boiling point, to the normal boiling point, but just don't let that freak you out if it decreases a lot. The only place to be freaked out is either A, if it gave you a higher vapor pressure than 1 atmosphere, then something's wrong, or B, if you got a negative pressure, because that wouldn't make any sense here. You would expect the pressure to be something larger than or smaller than 1 but greater than 0. Okay. I also suggest that doing these Clausius Clapeyron problems are really good things to work on because you're good at practicing some of the algebra skills. Because these are problems that one of the challenges could be rearranging things. For example, in some of the problems you might not know a temperature. Then you've got a variable in your denominator. And then in the easiest versions of the problems, you'll be looking for enthalpy of vaporization. And because that tends to make it simpler, there's nothing in the natural log that's a variable, and there's nothing in the denominator that's a variable. So those will be the easiest. But I suggest practicing a couple of these because once you get them down, they're very systematic problems that tend not to have hiccups that trip you up. But until you're practiced, they just take so long because it's just trying to keep track of, wait, where did this thing move? What do I do now? And it just takes a lot longer than after you've had some practice. And that can really help out in getting you through your tests. If you just do a few more of these, find them through your textbook or online resources if you're seeing my video from somewhere other than my class. But I think this is definitely somewhere to work on to help speed you up compared to everything in the class. Obviously, working on it can speed you up, but this is an area where I find it helps students the most, where the best bang for your buck. If you're not going to work in a lot of places, at least work on this one. I think it helps a lot. So with that, I will talk to you later.